Châtelier. This I don't think is going to give you too much trouble, hopefully. It's more conceptual than mathematical, so we're through kind of the big mathematical part. And it was a big mathematical part because it's the only time, I mean, you might have felt like you were in math class a little bit today when you were doing the quadratic formula. But as far as the Châtelier, basically, the difference between what we've done already, because we've talked about Q already, all right? Q versus K. Do you guys remember Q versus K? Did you watch that video? Is that the one from yesterday? I guess that is the one from yesterday. Okay. So that whole idea is when you first, usually it's like your initial concentrations when you're first starting a reaction and then it's going to equilibrium. Le Châtelier, you're already at equilibrium and then you mess with it. Okay, you're doing something to push it out of equilibrium, and then you're trying to figure out what that's actually going to do. Okay, so that's the difference between Le Châtelier and the Q versus K thing. All right. So if the system's at equilibrium and you change temperature, pressure, or concentration of one of the components, the system will shift its equilibrium position to sort of counteract that effect. Okay, so we're going to talk about how that occurs. The Haber process is really, really important to AP chemistry curriculum writers. They really like the Haber process a lot. I mean, it's very important just in general as well. Kind of revolutionized the agriculture industry because it's a way to mass produce ammonia. And that helps a lot with fertilizers and that sort of thing. So it is a very, very important process. So the way that when people started to realize that we can change pressure, we can change temperature, and we can mess with the equilibrium, they were able to apply it to this reaction, and they realized that if you increase the pressure, the amount of ammonia present at equilibrium will increase, and if you increase the temperature, the equilibrium decreases. All right, so what they realized was the ideal conditions for making ammonia from nitrogen and hydrogen gas is to make the temperature fairly low and put a lot of pressure on it. Okay, and if those two things were done, then you could greatly increase the amount of NH3 because you keep pushing the equilibrium towards the products. Okay. So this is basically what I just said. It's very important in agriculture. And so the reaction here, N2 plus 3H2 yields 2NH3. And that's the Haber process. So there's some different ways that you can mess with this equilibrium. Another way that you can mess with the equilibrium is by adding a reactant. So if we add H2 to the system, then the N2 will be consumed, and that's going to cause it to form more of the NH3. So essentially, you're increasing one of the reactants. Okay, if you start pumping more and more H2 into this thing, then it can react with the N2, and it can make more of the product, which kind of makes sense, right? So you put in more of a reactant, it pushes the equilibrium towards the product, so now that we're making more of the products. Okay. Now we're also limited by the amount of nitrogen we have, so you have to be careful with that. You need enough nitrogen gas, but that's usually not a problem because all you have to do is just gather some air, right? Look, I'm holding like 78% nitrogen right now. Not really holding it.
It's a really funny joke that everyone can see on YouTube.
Yeah, yeah. That's not going to work well on the video. Oh well. It was really funny, trust me, video people. All right. So here's an apparatus that helps push that equilibrium to the right or towards the products, okay? Because what it does, instead of adding reactants, it actually removes the product, okay? So if you think about this, if you've got this reaction that's happening here, I don't know why, but sometimes it just helps me to look at it this way. So here's your reaction. And actually, this is in equilibrium, right? So it's going in both directions at the same time. But if I take the NH3, and as soon as it gets produced, I move it somewhere else away from the reaction, well, now the only way this reaction can go is back towards the products, right? because I don't have any NH3 that can go back to the N2 and the H2. So as long as I keep pulling out the NH3, pulling it out and pulling it out as it gets formed, the N2 and the H2 continue going this direction, okay? So you can kind of force a reaction that's really, it doesn't make a lot of ammonia naturally, but you can force this reaction to go that direction just by continually pulling out the product as it forms, okay? So you've got all kinds of stuff going on here to move it through, but this is just kind of the apparatus, and it explains how you can even recycle the unused N2 and H2, but how we're basically removing the NH3 as this reaction occurs. And if you do that, then the N2 and H2 will keep reacting and keep reacting and keep reacting until you have a lot of ammonia. Okay, so Le Châtelier predicts that if pressure is increased, the system will shift to counteract the increase. It shifts to remove gases and decrease pressure, all right, which kind of makes sense. A system will attempt to be under the least amount of pressure possible, okay? This will make more sense once I show you some examples. But an increase in pressure favors the direction that has fewer moles of gas, okay? Let me show you an example of kind of what that means, maybe. In a reaction, if it has the same number of moles of gas in the products and reactants, that's not going to change the equilibrium at all. And if you increase the total gas pressure by the addition of a gas not involved in the reaction, that's not going to affect anything either. Okay, so it has to be a specific type of change. Really? Why is there not an example there?
Not really.
Sorry. Oh, okay, so it's going to ask us about all of them at the same time. So we'll get to the examples. The other thing you can do is you can increase or decrease the temperature, okay? And this is actually one that you guys get to do in the lab on maybe Tuesday. So basically, you can change the temperature of this cobalt chloride, and then you can change it from blue to pink, and you can actually change it back and forth, back and forth. You put it in the ice, it'll change pink. Put it back in the hot water, it'll change blue. You can just keep doing this over and over again. And the reason that that happens is because you've got two, you guys remember learning about coordination complexes or complex ions? You've got two complex ions that are formed in this equilibrium, okay? One of them, the COH2O6, that is more of a pink color, okay? The COCl42- is more of a blue color. So there are several ways you can mess with this equilibrium. Actually, one of the ways you can mess with it is by adding acid, well, adding HCl, I guess, or adding extra water. Because if you add extra water, it's going to tend to form this ion, okay, which is going to make it more pink. If you add more HCl, now you've got more Cl- ions available, and it can form this complex, and then it's going to turn bluer. Okay, so you can shift it back and forth by doing that, but you can also do it by changing the temperature. And with temperature, notice the delta H for this reaction is greater than 0, which means it's what type of reaction? Endothermic, right? Okay, it's a positive delta H. That's going to be endothermic. So could we maybe say, instead of saying delta H is greater than 0, could I also say that, whoops, I couldn't say that. Could I also say that heat is maybe one of my reactants? It's kind of a different way of thinking about it. But are you guys okay with that? Because in an endothermic reaction, I need to add heat for it to occur, right? So I could kind of see heat as being one of the reactants. So if I already said adding a reactant pushes the equilibrium towards the products, if we add heat, that's going to push the equilibrium that direction, right? If you add heat, what color is it going to turn? It's going to form more of this, which is the blue, okay? So it's going to turn bluer. Put it in the ice water, okay, now I'm removing a reactant, which pushes the equilibrium back this direction. So now there's more of the COH2O6 complex, and that's going to turn it pink, Okay, so you can actually do this by temperature as well. I think you guys are going to like this lab because there's basically just 6 different reactions that are like that, where you're just messing with the equilibrium and making, primarily color changes and that sort of thing. But hopefully you guys enjoy it. But that's kind of the idea with temperature. Okay, so those are the 3 basic things that we can do to mess with an equilibrium. We can mess with the concentrations of either the reactants or products. We can change the temperature, or if we're talking about gases, we can change the pressure. Now in this reaction right here, changing the pressure over the reaction is really not going to do much. Okay, if you have a gas reaction, that's where changing the pressure is really going to have an effect. Okay, so here's our reaction. We've got this equilibrium right here. It's a gas reaction. We've got a delta H for it. So we want to know what direction will the equilibrium shift when each of the following changes gets made to the system at equilibrium. So if we add N2O4, so if I'm basically pumping more N2O4 into this thing, which way is that going to push the equilibrium? It's going to shift it to the right. Okay. What about if I remove NO2? Okay, also to the right, because I'm pulling out the product, so then more product will be formed. Okay, so that shifts the equilibrium to the right as well. Increase the total pressure by adding N2. Okay, so if I increase the total pressure in this container by adding some N2 gas into it. N2. Sorry. Yeah. So what would that do? It's a totally different gas. It's not part of the equilibrium, right? So it's really not going to affect anything, okay? We're still going to have the same partial pressures of each of the gases that are in the reaction itself, okay? So that's really not going to have an effect. But, you can ask a question? Even if it's in a closed container. I know that's a little weird because we are increasing the total pressure, right? But what you have to remember, we're not increasing the pressure of either of these 2 gases, and that's the main thing, okay? But let's say that we increase the volume. Now what did we do to the partial pressure of these 2 gases? We decreased them, right? We decreased it. Yeah, we decreased the pressure of each of those gases, okay? So this, I think the decreasing the pressure is a hard way to think about it. So let's think about the opposite for a second, okay? Let's say instead that we had increased the pressure of each of these, right? Which way is the equilibrium going to shift if we increase the pressure? If we had increased the partial pressure of both of these by, let's say, decreasing the volume of the container instead, so we're compressing it, then which direction would the equilibrium have shifted? To the left. And the reason for that, okay, there's less moles of gas on this side, right? Okay, so the equilibrium is going to shift in the direction where it can decrease the pressure as much as possible. Okay, so you're increasing the pressure of both of these. That's going to push the equilibrium back towards the 1 mole of gas, because now you just have 1 mole of molecules bouncing around as opposed to 2 moles of molecules bouncing around. Does that make sense? Okay, so that's if the pressure was increased because we decreased the volume. But we're doing the opposite of that. So if we increase the volume instead, then it should shift the equilibrium in the other direction. Okay? I think it makes more sense to think about the increase in pressure and then just do the reverse of that. What about if we decrease the temperature? Okay, so where's heat on this one? Part of the reactants because it's endothermic, right? So just like the last example that we had, heat is basically over here, okay? If we decrease the temperature, we can kind of think of that as removing heat, right? We're removing a reactant, so which way does that push the equilibrium? Towards the reactants, right? Okay? Now, I should look and see if it's in the notes. Effective temperature on K. No, sure not. Oh, okay, here we go. Use this result to determine how the equilibrium constant for the reaction should change with temperature. Well, let's talk about it over here, okay? So let's say instead of the question being what direction will the equilibrium shift, let's say that I'm asking instead how is it going to change the equilibrium constant? Because I don't know if you guys remember this, the only thing that changes the equilibrium constant is temperature, okay? And do you remember what the reason for that is again? What is the equilibrium constant really? It's not a ratio. Well, okay, it is a ratio of concentrations, but how did we derive it in the first place? How did we get that actual K? It's the ratio of the rate constants, right? The forward and reverse rate constants, okay? And those rate constants also change when temperature changes. We learned that in the last unit, okay? So that's why the equilibrium constant is affected by temperature. So the K actually changes if we do something to the temperature. That's the only time that the K changes, right? For the rest of these changes, right here, we're not changing the K, we're just changing the concentration ratio of the reactants or the products, okay? But on this one, with the temperature change, we're also changing the K. So how would we be changing the K on this one? Let's say that we decided the equilibrium was shifting, nope, I'm sorry. We decided the equilibrium was shifting, oh no, we did decide that, didn't we? I forgot which one we were talking about. So we decided the equilibrium shifts to the left. If I wrote the equilibrium expression for this one, it's the pressure of the NO2 squared over the pressure of the N2O4. All right? So if the equilibrium is shifting back this direction, so that now I have more of the reactant, what does that do to my K value? It's going to decrease it. It's going to cause it to go down, okay? So if they ask you that question, if they ask you what happens to K if we decrease the temperature, there is not one right answer to that question, all right? It depends on whether it's an endothermic or an exothermic reaction, okay? Because in an exothermic reaction, our arrow would be pointing in the other direction because heat's on this side, right? If we're removing heat in an exothermic reaction, it would actually push the equilibrium towards the products. Does that make sense? Okay. So that's how K changes based on temperature. Let me see if there's anything else. Temperature's decreased, volume of this.
Okay, what about
PCl3.
temperature change when you add heat to it?
What about the temperature change when you add heat to an exothermic? Or meaning how the K changes?
Yeah.
Okay. So let's say this is exothermic. This is a negative 58 instead. It's not, but let's just pretend that it is for a second. So you said if you add heat.
Well, for this one it'd be.
Okay, so if you decrease the temperature, pushes the equilibrium this way, right? Because we can think of that as pulling out a product. So if you pull out a product, it's going to shift the equilibrium towards the product side. So again, thinking about I'm going to write it down here because I have a little more room here. Thinking about our expression, if I'm shifting towards the NO2, that's going to increase K. All right? So you decrease the temperature of an exothermic reaction, K increases. You decrease the temperature of an endothermic, K decreases. I wouldn't memorize that though. I would just think about it in terms of, think about your equilibrium expression, think about which direction the equilibrium is shifting, and think about how that would have to change K. Because when we change the temperature, I don't know, I'm going to say that. I'll just leave it at that, okay? Does that make sense? Sorry.
This is one of those battery questions.
Yeah, that didn't work out well, did it? Okay, using the standard heat of formation, determine the standard enthalpy change for the reaction. Determine how the equilibrium constant for this reaction should change with temperature. Okay, so this one, basically they're asking you to just do an additional step there where you find the standard enthalpy change. So if you look in the back of the book, I don't know if you guys remember this, but the standard heat of formation would be forming 1 mole of the product. You guys remember that? Standard heat of formation is for when 1 mole of the product gets formed. Since this is 2 moles, you have to multiply that number by 2. So that gives you the negative 92.38. But it's still exothermic, okay? So based on what we just did, that's going to shift the equilibrium this direction. Oh, guess what? This is an exothermic reaction. You remember me saying that, wait, did I do that wrong? It says how it should change with temperature. Okay, so it doesn't even specify which way. So like in the previous example, if we decrease the temperature, it's going to push the equilibrium this way, right? Is that consistent with what we said at the beginning about the Haber process? When does it work the best? That was actually at lowest temperatures, right? That's when the Haber process works well. So that kind of makes sense, right? This is an exothermic reaction. So we decrease the temperature, that's going to push the equilibrium towards the NH3, which is what we want. At highest pressures. And the reason for that, we can also look at this, right? So you put a lot of pressure on this thing. Which direction is it going to go? Towards the side with the least number of moles, right? Which is the product side. The reactant side has 4 moles of gas. Okay? The only other thing I think I need to talk about, and I wish I had the... Oh, wait. This is the last section, so we need to talk about catalysts also. Forgot about that. Catalysts are going to increase the rate of forward and reverse reactions. Okay? So what you need to know about catalysts is that they help you get to equilibrium faster, but they don't affect the position of the equilibrium. Okay? They're not going to change the equilibrium constant or anything like that. They're not going to change the concentrations you end up with at the end. A catalyst just, because it makes both reactions happen faster, then that means that it's going to just help the reaction reach equilibrium more quickly. Does that make sense? So it's not going to change the equilibrium in any way. It's just going to get you there faster. And I think, oh, there's a big X through that. So I guess not. Okay. Here's the one other thing that I wanted to tell you. And I wish it was on here. And actually what I wish is that I had thought ahead enough to pull up the... You guys have your reading guides out? You taking notes on them right now?
Yeah. Maybe.
Here. I'm going to pause this for a second because I think this is worth finding. Why is this not...
Oh, we don't have time to explain that.
All right. So this is what I wanted to show you here. The Enduring Understanding, I think, does a really good job of explaining this. Systems at equilibrium are responsive to external perturbations, kind of an interesting word, but the response leading to a change in the composition of the system. So, in other words, you perturb the system, you bother it in some way, okay? And what happens here is you change the rate of the forward and reverse reactions. That's ultimately what's causing the change, okay? So you can cause that rate of the forward and reverse reactions to fall out of balance. That's called the stress on the system, okay? So the system then is temporarily out of equilibrium, and then it's going to work to get back to that equilibrium state again, okay? That's referred to as a shift of the chemical reaction. So when I say that it's shifting to the right or shifting to the left, the equilibrium, that's what I really mean, okay? It's affecting those reaction rates, causing them to be out of balance temporarily until they come back into balance, okay? The other thing that I wanted to point out here, I think it was 6B2. Disturbance to a system at equilibrium causes Q to differ from K. So you can think about this in a Q versus K sort of way as well. Okay? Taking the system out of the original equilibrium state, system responds by bringing Q back into agreement with K, thereby establishing a new equilibrium state. Okay? Okay, here it is. Some stresses, such as change in concentration, will cause a change in Q. All right? So you change the concentration by adding a reactant. That changes Q. It's going to work to get back to K. Now, if you change your temperature, that changes K. All right? So now Q and K are different because the K changed. So then the reaction will shift in either way, either case, to bring Q and K back into equality. I thought that was a good way to explain it, so I thought I would show that to you guys. But that's pretty much all you need to know with Le Châtelier, I think. It's really not all that difficult. It's a lot more conceptual, not as math-based. And that's basically what we're going to do the lab on Tuesday. Okay? All right. We'll see you guys in class Monday.